if I enlarge this triangle, I get something that looks like this. We've established that our delta S parallel is our change in vertical position, our delta Y. And of course we have our delta S vector here, which has been projected onto the gravitational force vector. What do we know about this triangle? Well, somebody said to me, well, it's a right triangle. This is a right angle because when we project at a right angle. What else do we know? Well, somebody said we know delta S, and I disputed that. We don't know delta S. We do have enough information to find it. If we know an angle and the delta S that we will easily be able to find just using the definition of a radian, and we'll do that right here, then we're going to easily be able to multiply the magnitude of the displacement by the cosine of this angle and get our delta Y. Okay. In order to figure out what this angle is, well, let's go back to our big picture. We know what theta is. It's approximately 4.27 radians. Okay. So, what angle does delta S make? Well, delta S is tangent to the curve, or approximately tangent. The chord from here to here is practically a tangent to the curve. So what angle does that mean delta S makes with the gravitational force vector? That's going to be the angle we want here. In order to figure out that angle, we can find the angle of our R vector with horizontal. Okay? That's just going to be theta minus the 180 degrees or pi radians that you have to here. So if this is 245 degrees, 245 degrees minus 180 degrees is 65 degrees. Or alternatively, if this is 4.27 radians, which is accurate, 245 degrees isn't, if this is 4.27 radians, we subtract pi radians, which is the angle here, instead of 180 degrees. Okay, so in the picture I have here, I've taken the radial direction. This is implicitly the center of the circle. This is a line, the line through this point in the center. And it makes an angle theta minus pi with the positive x-axis, with the horizontal. The tangent direction is perpendicular to this direction because tangent to circle is perpendicular to a radial line. That's a simple result from high school geometry. Putting those two things together in a way that you really need to reason out, maybe in terms of this picture, maybe in terms of your own picture, we determine that this angle is theta minus pi, 4.27 minus pi, 1.13 radians. Okay, this is the angle that's the 1.13 radians. And we have to distinguish, is it this angle or some function of either of those angles. Very simple. This is the angle. So here's our delta S. If we know the magnitude of our displacement vector, we multiply by the cosine of 1.13 radians. And cosine of 1.13 radians is a little over 60 degrees. I think 63 degrees or so. Let's see, 1/7 of 56 is 8, so it's more like 65 degrees, if I did that right. So my 245 degrees actually looks pretty good, but I just pulled that out of a hat. No insight involved. Okay, end of digression. We need to figure out delta S. If we can figure out delta S, we can figure out delta Y. You're given the gravitational force, that's 800 newtons downward. So if we get this component of delta S, component parallel to the gravitational force vector, we multiply the two, we get the work done by gravity. Okay, well, very simple. in terms of definition of a radian, magnitude of delta S is just the radius of the circle times the change in the angle, times your 0.01 radian. 7 meters radius times 0.01 radian. Now you have to understand radians and so forth. So I'll probably talk a little bit about that and why that works. But that gives us 0.07 meters by the definition of a radian, essentially. So this is 0.07 meters. This is about 1.13 radians. It turns out that our delta S parallel is going to be between 0.03 and 0.04 meters. Multiply that by, well, you multiply our 0.07 meters by the cosine of this angle. Probably closer to 0.04 meters. No, 0.03 meters. Okay. Well, that's pretty much it for this picture, but we need to try to work out this picture. Now we're working the White's-Mill experience into some preliminary work on rotation. And we're doing it from a physics standpoint and from the standpoint of energy, which is why I asked to find the change in potential energy. Okay, next I'm going to just talk a little bit again about potential energy and how the change in potential energy being equal and opposite to the work done by the conservative force implies that if your potential energy decreases and there are no non-conservative forces, then the decrease in potential energy will be equal in magnitude to the increase in your kinetic energy.